In this lesson, you will identify forces and examine the nature of forces, draw force diagrams, distinguish between contact and non-contact forces, calculate the resultant of parallel forces, investigate the effects of frictional forces, and demonstrate a basic understanding of weight. The key concepts covered. We will look at forces, force diagrams, free body diagrams, frictional forces, frictional coefficients, and weight. The nature of forces. What is a force? A force can be defined as a push or a pull. A push or a pull. There are two main types of forces. Firstly, contact forces. These are the normal force, frictional force, tensional force, and the applied force. The other type of force is the non-contact forces, and these are gravitational forces, electrostatic forces, and magnetic forces. A force is a vector quantity, and it therefore has magnitude, which is a value, and direction. The unit of force is the Newton, represented by a capital N. We're now going to look at force and free body diagrams. The definition of a force diagram is a drawing of the object of interest with all the forces acting on it represented by arrows. Here we can look at an example of a moving box. There's the box, the applied force represented by a vector, an arrow, and a capital F for the applied force. In the opposite direction we have the frictional force with a lowercase f. This is a force diagram. The definition of a free body diagram represents the object of interest as a dot, and all the forces acting on it as arrows pointing away from the dot. Example, the same moving box represented by the dot, and there's the applied force with a capital F and the frictional force in the opposite direction. Now we look at the resultant or net force. A definition: the resultant or net force of the object of interest, and we represent resultant or net force as F_res or F net, is the sum of all the forces acting on it. Let's have a look at that. Suppose two forces are acting in a straight line, F1 and F2, both in the forward direction. If they are both acting in the same direction, they are added together. So your F resultant or your F net will be equal to F1 plus F2. They're in the same direction. And then we would have a resultant force of the sum of F1 and F2. Now, if they are acting in the opposite direction, they are subtracted. For instance, F2 in the forward direction and F1 in the opposite direction, we would then have the resultant force will be in the direction of the largest force. In this case, you can see F2 is larger than F1, so your F_res or resultant force will equal F2 minus F1, which would give us a resultant force in the forward direction. You see, a resultant force causes a change in the state of rest or uniform motion of an object. We can see in example 1, a resultant force can cause a stationary box to accelerate. Stationary meaning at rest, and if the resultant force, the F net, can cause the box to accelerate from rest to accelerate. In example 2, the resultant force can also cause a box to decelerate. A moving box, F net, and the box can stop, decelerating, accelerating, and decelerating. If there is no resultant force when the F net or F resultant equals 0, then all the forces balance, and we say the forces are in equilibrium. Let's have a look at balanced forces. Consider the book on a table. The earth pulls the book down with a force Fg, and if the table was not there, the book would fall. Looking at the balanced forces with the table on the book. Since the book does not move, the table must be pushing up on the book. The force up, which we call the normal force, equals the weight of the book down. Normal force up, force of gravity Fg, or the weight downwards. And since the combined effect of these two forces is 0, we can see that the F net, or the resultant force, will equal 0 newtons, since the normal force, upwards, equals the weight downwards. So if an object is stationary or at rest, or if it's moving at a constant velocity, we can say that all the forces acting on that object are in equilibrium. Let's look at stationary objects, or objects at rest. The weight Fg of an object is balanced by an equal force exerted by the table, called the normal force. Here we have a stationary object. Weight down, Fg, equals the normal force upwards, and therefore the object will be stationary. If the friction and the applied forces are equal, an example of this is when a person is pushing a truck, there is no movement, and for example, firstly in the vertical direction, the weight downward, Fg, is balanced by the normal force upwards, so the vertical forces are in equilibrium. And then in the horizontal direction, we have a 100 Newton applied force balanced by a 100 Newton frictional force, and therefore there would be no movement. So the vertical and horizontal forces are balanced. If we examine moving objects, let's look at the case where there are balanced forces. In this case, consider a box with the vertical forces balanced, the normal force balanced by the weight of gravity, and we have 5 newtons applied and 5 newtons of friction in the opposite direction. If the box is moving at a constant velocity, the applied force keeps the object moving at a constant speed, and the resultant or net force is 0. If we look at when there's a net or resultant force, for example when the normal and weight are balanced, but there's 5 newtons of friction but 8 newtons of applied force, the applied force is greater than the force of friction, and therefore the object will accelerate. There will not be a constant velocity, there will be an acceleration. Looking at challenge 1. Consider a box on a table and the horizontal forces acting on it. We're now going to calculate the F net, or the resultant force. Looking at these examples, box on a table, 5 Newton force in that direction, 3 Newton in the opposite direction. Calculate the F net. Example B, 5 newtons in this left direction, another 3 newtons in the direction to the left, and what would its resultant or F net force be? Example C, 5 newtons to the left, 3 newtons to the left, and 10 newtons to the right. Now stop the DVD and calculate the F net and then check your answers. Looking at the answers, example A, the solution would be 5 newtons to the left, 3 newtons to the right, therefore the F net would be 2 newtons to the left. Example B, 5 newtons to the left, 3 newtons to the left, resultant F net 8 newtons to the left. And example C, you can see the F net would be 2 newtons to the right. We hope that you got all those examples correct. An introduction to weight. The weight of an object is the result of the downward force that the earth exerts on the object, called gravity. Here we have the earth and an object on the earth's surface. It's pulled towards the center of the earth with the force of gravity. We represent weight by a capital W and gravity by F and a small g. The weight equals the force of gravity that Earth exerts on the object. Therefore, weight equals Fg. If we calculate weight, we use the mass of the object m times the acceleration due to this force of gravity g. And little g is the acceleration towards the center of the Earth, and therefore small g is 9,8 meters per second squared. And if we multiply the mass of the object times the acceleration due to gravity, represented by g, we will get the weight of the object. Let us examine friction. When two surfaces slide over each other, there is resistance. Resistance is due to the frictional force. Friction may produce heat or noise. An example, when rubbing your hands together or scratching two metals. Friction opposes the sliding motion, acting parallel to the two surfaces. Resistance due to friction can depend on three things: the type of material, the roughness, and the normal force. This is the force pressing the two surfaces together. Calculating the frictional forces. Friction is represented by the following relationship. Frictional force equals, this is a symbol for coefficient of friction, times the normal force. So F is the maximum friction force. F with a subscript n is the normal force, and this symbol is the frictional coefficient. We use this formula to calculate the frictional force. Friction coefficients. There are two types of friction. Firstly, we get static friction between two objects not sliding or moving against each other. Then we get kinetic or dynamic friction between two objects that are sliding or moving against each other. For static friction, we use a static coefficient of friction represented by the following symbol with a subscript S for static. For kinetic friction, we use a kinetic coefficient of friction represented by the following symbol with a subscript K. Static coefficient of friction and kinetic coefficient of friction. In calculations of friction, we use the frictional coefficients. The static coefficient of friction represented by this symbol, is used in the following equation. For an object at rest, the frictional force will be less than or equal to the following product: the coefficient of friction, the static one, times the normal force. The kinetic coefficient of friction, represented by that symbol, is used when an object is in motion. So the frictional force in this case for an object in motion will equal the kinetic coefficient of friction times the normal force. We're now going to do an example involving coefficients of friction. Challenge number 2. A man tries to push a box which has a mass of 10 kilograms across the floor. The coefficient of static friction, represented by this symbol, equals 0,4, and the coefficient of kinetic friction equals 0,3. Remember, this is static friction when there's no movement and kinetic friction when there's movement. Now we need to calculate the frictional force F exerted directly on the box if there's an external horizontal force F exerted by the man of 10 newtons, 20 newtons, and then 40 newtons. Let's examine that in a diagram form. We have the normal force and the force of gravity. This is the vertical direction. And the horizontal force, the applied force, and the frictional force. Now we're going to look at challenge 2 solution. We suggest you stop the DVD and do the calculation, and then view the DVD and check your solution against the answers presented. Looking at the vertical movement, there's no vertical movement, and the Fn equals Fg, and you can calculate mg as 10 kilogram, the mass of the box, times g, 9,8 meters per second squared, and we therefore get 98 newtons. Now looking at calculation A. The static frictional force will oppose the external force with a maximum of, and we're going to use the formula, F equals static coefficient of friction times force, normal force. We've calculated the normal force to be 98 newtons, and we were given the static coefficient of friction to be 0.4. Calculating that, 0.4 times 98, and we get 39,2 newtons. Now remember, the applied force is 10 newtons in example A, and therefore the box will not move because the friction F will be as large as the applied force, and therefore friction will be 10 newtons as the applied force is 10 newtons, and the box will not move. The applied force in B is 20 newtons. It's still not large enough to actually make the box move. Let's examine this. The frictional force, calculating using the static coefficient of friction and the normal force, we see is 39,2 newtons. The applied force is only 20 newtons, and therefore the box will not move. Remember, the frictional force will be as large as the applied force and will be 20 newtons, and to get the box moving, it must be, applied force must be greater than the frictional force. Looking at solution C, when the applied force is 40 newtons, it will cause the box to move because it is larger than the static frictional force. Remember, we calculated the static coefficient friction was 0.4, and we calculated the friction to be 39,2 newtons, and since the applied force is 40 newtons, the box will move. Now, using the kinetic frictional coefficient as 0.3 and the normal force is 98 newtons, we see the kinetic friction will be 29,4 newton. The F net equals the applied force minus the frictional force. In this case, it's equal to 40 newtons, the applied force, minus the frictional force which we calculated as 29.4 newtons, and therefore we get an F net of 10,6 newtons. Since the applied force is greater than the frictional force, therefore the box will accelerate. To complete this lesson, here is a summary of the equations used in the calculations for this section. Remember to practice as many examples as you can from the section and revise the concepts from your textbook. Re-watch this DVD until you are confident of this section, and remember, have fun with physics and practice as many relevant examples as you can from this section.